take a look. Oh, so we talked about this Git stuff yesterday, right? How to have repositories and how to collaborate, and how all this works in practice. So if I could get all of you first to go to the course Git repository. In my case, it's right in my home directory, 2013 09 16 ISI. If I could get you all to go there. So last night and 3 minutes ago, I was finishing the materials for this section. And so what I've done is I have a branch on the GitHub repository on GitHub that I pushed to that has these new changes that you do not have. And so I just want to show you sort of a workflow of what happens. So what's happening is I'm furiously banging away at things the last minute. Then you go to GitHub, and you can see all the branches we have dangling around. And there's this numpy one, which was updated 4 minutes ago. And I can issue a pull request. So with this branch has all of the development work I've been doing on getting the materials for this numpy section that I'll teach. And so this adds some files, it moves some directories, it gets things ready. So all of this happens outside of the main repository. And so I'm going to issue this pull request, which alerts the owner of the repository, who I also happen to be friends with. He's right in the back of the room. And don't merge yet. And so now we can see that there's this outstanding pull request, which says I have some work that I've changed that I would like you to bring into the repository proper. And so if we have a look at this, maybe making comments. Okay. What this does is it starts a conversation about the code I've just sent. Right, so it tells you all the commits that happened with the commit messages, and so looking over this, you can see what files changed. Right, you can snoop through all of the things that happened. And then Ariel has looked at it and said that, okay, this looks good to go. And we can go ahead and merge the pull request. Oftentimes, you cannot merge your own pull request because you're submitting pull requests to a repository you don't own or not collaborators with. But I'm a collaborator on this one, so I'm going to go and do it. Okay, great. So now this is in our main repo. We look at the commits. We can see that I've added a couple things. So now we need to get all of this on your machines, right? Because you don't have this yet. This happens someplace completely separate from you. So I want you to go back to that directory that has your Git repo in it. Make sure you're on the GH pages branch. Type git pull. And you should see some stuff like this. It tells you that some files changed where and now, everyone good? Green. We need to pass out more green stickers. So let's pass out some stickers because we're going to want these. So this is not work for you. Please stick up a hand and wave it around so we can come help you, because we will need these materials for the rest of the Worked on the first try. I have conquered the gods of live demos. First rule of live demos is never do a live demo. Let's continue on. So you're in the repository, and I want you to go into the lessons directory, and then into the numpy directory, which didn't exist as of 2 minutes ago. So you should be able to go there, right? You see some green stickies when you're all there.
Where, I'm sorry?
So go to the lessons /numpy directory.
Sorry, I missed the first part. How do you get the numpy?
So did you do the clone? Did you do the pull?
I haven't.
Okay, so do that. So make sure you're in the repository.
Yeah.
And then you're going to type git pull. It should show you stuff that looks like this.
Yes.
And then now go to the lessons numpy directory. Okay. Now, just git pull. Good.
More.
Okay. So now that we're here, we're going to fire up another IPython notebook. Python notebook. And you should see something that looks like this. Again, everyone's with us? Let's open up the numpy notebook. No. Okay, all set? A couple things, and I think, Ariel, are we ready to go? Okay, so we're going to talk about numpy. So we talked about the core Python language yesterday, right? We talked about lists and dicts, and strings, and all these kinds of stuff. And so now we're going to start talking about some of the broader scientific computing libraries. So numpy is an array for dealing with typed n-dimensional arrays, which you've probably seen if you've done any other computing. So what these are is they're typed. We'll pack this off piece by piece, which means that every element in the array has the exact same type. And so most of you, that probably means it's a float or it's an int, right? That you've gathered some data in the field and you've measured something that has a value of 3 or 3.7 or something, and you're processing that data. They're n-dimensional. So when we talked about lists are one-dimensional. There is just one axis. You start from 0 and you go to 3. N-dimensions means there can be multiple dimensions. So if you first think of a vector, right? A vector has one dimension, and a matrix has 2. So you now can index by an I and a j. And you could generalize that to 3D, I, j, k, and to as many dimensions as you want. So this is super useful because if you're doing a 3D simulation and you need indexes for all 3 physical dimensions, you're good to go. If you're doing it in 6 dimensions, then you have a velocity component of each. Now you can easily describe that. Okay, so that's what n-dimensional arrays are. And NumPy is a library that provides fast and easy access to these. Let's make some stuff. We need you to type more. So let's execute. Let's make some numpy arrays. Oh, what did I blow up? You must first import numpy. Very important. It'll complain that it doesn't know what np is otherwise. And then execute this first cell. And so we see first a couple of things. So numpy provides this array function, which if you give it a list, or actually any iterable thing, it will turn it into an array. We also start poking around these and seeing what sort of attributes are on array, and it has this d-type thing, which is a float 60. And so what this is it's a d-type is a data type. This is telling you what sort of in hardware on the actual processor, how these things are represented. And so it's a 64-bit floating point. It could be a 32-bit, it could be a 64-bit int. There are a bunch of different types that these could be. If you want to make sure that a specific array has a particular type, you can just tell it, I want d-type to be int. And they come out as ints. Exactly how int is written, if int is a 64-bit or 32-bit int, is sort of depends on your particular machine. But that's just what you get. So NumPy has a bunch of convenient functions for creating arrays. There are things like identity, which will create the identity matrix. There's zeros. There's a function for zeros like, which takes an array and returns an array of zeros that has the same shape thing it started off with. And empty, which just allocates a buffer and doesn't zero anything out. So you'll just have crazy floating point numbers to start. So first exercise, I want you to create an array with 8 elements, and I want them all to be ones. Also remember in IPython you have tab completion, so you can go searching for things that might look interesting. Ready, set, go. Okay, so let's move on. So if you saw that NumPy has a zeros, you may have guessed that it has a ones. Super helpful, and I want, so doesn't want the shape, so we'll give it 8. We can print that. And they are indeed all ones. We could say B is zeros like A, and that would do something similar, right? We could have also said B is A minus 1. Right, there's a bunch of different ways we could have done this. So let's keep moving. NumPy, so we sort of skipped over range, but Python has a built-in function called range. And NumPy has a similar version called arange, but instead of giving you a Python range, it gives you back a NumPy indie array, right? So this is a common, another type of array you're often going to want to do, right? You have a bunch of data points and you need to generate an index for them, right? That's super. So a range also also has a bunch of other ways you can customize how it creates. So by default, it steps from the beginning, from the first index to the last index, in increments of 1, but you can customize that. So why don't you now create an array that steps from 0 to 10 in increments of by half. Remember that, so you can look at the numpy documentation if you don't see that. Also remember that you can type question mark if you want some help on a particular function. So give me an array that goes from 0 to 10 in increments of by half. And give me a green sticky when you're good. Okay, so if you got in here and started playing around with things, you probably would have just typed the easiest thing first in A range. That gives you in increments of 1. And if you hit the right combination of keys, you may have seen this little tooltip pop up that gives you some information that A range goes from start to stop, an optional step.
What's the right?
Hit a tab.
Yeah.
Yeah, like when you're there, try and...
I just have those really square brackets there.
So the square brackets denote that they're optional, that those options are optional. So so in this particular case, if you do A range, and then the first number is start, which is optional. So if you just do A range of 10, it'll assume 0, go 0. If you give it a start, it'll go from 4 to 10. And then a step is the third argument. So in our case, we want a step of a half. And there we go. Sorry. So hopefully you're starting to get a flavor for how to create arrays, how to make the pieces that you need. So I've mentioned data types, but let's cover it in a bit more detail. Computers represent numbers in very particular ways. And they represent them in ways that are not platform independent. So your particular processor will represent a floating point number in one way, whereas an old Mac Power PC would represent an entirely different way. And if you have an Atom processor in like your iPad, that probably does something different. And so I guess those aren't atoms; those are A7s. Anyway, but if you use the way your hardware natively represents information, things go fast. You can represent data much more succinctly on the hardware, and things go much faster. So what this starts to look like is C in a problem, right? And if you've written C, you have to actually declare types that correspond to your physical part. And so this is actually what's going on under the hood, is as NumPy is sort of a thin veneer over high-quality algorithms written in C and Fortran, very little. Yeah?
Make an array, and one of the cells is a real number, like 77,
Yes.
what does that mean? So an array with a floating point.
So,
and are you sure there was small? The
Yep.
small was not. What does the big type not mean?
So I think the question is, in this particular line, let's use this for example, I'm creating an array B, and I'm giving it a D type. I'm saying this will be an array of ints. But the array I'm passing into it has floats. So in the case of A, NumPy can go inspect the elements and choose a sensible D type. But in this case, I'm telling it a D type, and so what's going to happen is it's going to go through and convert each one of these individually into an int. Because I've said this will be an int array. And so in this case, the 2.3 gets truncated to 2. So something really sweet. My apologies. Great question. Thank you. Okay, so D types, these are actually representing what's going on in your hardware. Let's move on to list operations. So NumPy arrays are sequences. You should be able to do normal sequence operations. So another exercise, hit the link. Change the third element, and yeah, do these two operations. You should be able to figure it out.
I have to.
Okay. I'm kind of lost myself, but I'll try to. Are you guys doing an exercise right now? I found out. No. You are? Okay, good. What are you doing?
Figure out the length of A and change the third element.
Good. Sorry.
I can take it over.
Acknowledge right.
Yes.
about that. I just got 4 calls about someone's car being towed in Wisconsin. It's not my car. I don't live in Wisconsin anymore. But I was a little paranoid. Okay, so so list operations, right? We should be able to ask for the length of an array because it's a sequence, right? That makes sense. I should be able to index these when I get the third element. This is 3 because it's a range. 2, right? And I should be able to set that equal 18 and print 2. Right? All of these things work. No black magic. Same interface you had for lists works for these 2. So let's do a little bit of arithmetic. Again, we're going to let you discover most of this yourself. I've created. Well, let's do something interesting first. Okay, so let's make a new array B. So you have to type along with me. B is numpy dot a range, and we'll make it 10. Print B. So I mentioned before that numpy arrays can be n-dimensional, right? So I should be able to make another, to take B and reshape this. And let's make it 2 by 5. So what's happening now is I'm taking this array that used to be 10 elements long, and I'm instead going to make it basically a matrix, where the first axis has 2 elements, and the second axis has 5. And so there's a total of 10 elements in that whole. So we can make B, we print B, it's now 2D, right? And now we introduce a slightly different notation for how to index. So if we just ask for the 0th element of B, it gives me a 5-element array, right? Because B is now 2 by 5, and so just the first thing, if you just ask for the first element of that, it looks like now an array. But we can also index directly into that and say, give me the 3rd element. Oh, right? So this should be familiar if any of you have done like MATLAB or array kind of stuff. If you're coming from or Fortran, if you're coming from a C world, you would have something like this instead. But this is much more convenient. So many fewer brackets. Yep.
Then you put just B0. Why the output was different? Just one dimensional array. After first running B.
Yep.
And would you want to get B0?
Yeah. So this. Right? So what's happening, so if you look at print B, which is this, right? This looks like a list of lists. It's implemented different on the hardware, but this looks like a list of lists. And so when you only ask for the first index, it's giving you back the first list, effectively. And so it's a subarray. It's actually technically called a view, and I'll talk about that later. But I just want to expose you to this notation. Yeah.
So
Correct. This is NumPy specific syntax. Right. Python lists are one dimensional. So if we had made, so we'll call it list of lists, right? 0, 1, 2, my list. Right? and I can access lol of 0, but lol of 1 doesn't make sense because lists and Python lists are only one-dimensional. Okay. Okay. So arithmetic. Create.
You said work with math.
Python proper does not do matrices. Python is a general purpose language, and if you're writing web servers, you don't care about matrices. And so, in general, the design philosophy of Python is to have the core language very small and have lots of libraries that handle specific things.
Oh, okay.
Okay. Let's do some arithmetic. So here's a couple arrays, A and B. Multiply them, add them, divide them, exponentiate them. Go crazy. Ready, set, go. Give me, once you've finished a multiply, a divide, an x, give me a green sticker. A few things about numpy arrays that are a little different than Python lists. First of all, numpy array operations are element-wise. So we take the first case, let's take the array A, and if we multiply it by 2, I get an element-wise multiply by 2. For comparison, I made a mylist, which is sort of the same thing, the equivalent thing, but a Python list, and I multiply that by 2. And instead of getting an element-wise multiply, I get the same list concatenated on itself twice. Right? Very different. And the reason is, Python lists are heterogeneous. They can be anything. Doing element-wise math operations don't make sense. But for numpy arrays, where we're really talking about math, we're talking about arrays and this kind of stuff, the thing that makes the most sense is element-wise operations. And likewise, when you start doing array operations on between arrays, right? So you could multiply a scalar by an array, and that works, and it does the thing you'd expect. You can multiply two arrays by each other, and it does the element-wise multiply. You can divide, and you can exponentiate, and things are all elements. So you may have seen this. This should yell at you if you do a divide by 0. Maybe it's not. Okay. It'll just like that. I don't know what's going on. So, okay. So, we have arrays. Yeah, question? Just subtract A minus 2, A minus B, because print A, print B, they're all 0 minus 5, 0, 1 minus 6. Right? So subtraction works, all of your normal operations work like you think. Okay, comparison. So in plain Python, right, we've done things like A and B equals 1, 2, and I compare is B, I can do comparisons, right? For a numpy array, when you have this collection, what does comparison really mean? And you may have taken a hint from the previous section that comparisons, again, are element-wise. And so what this will do is if we can make A and B, right, so these are slightly different, and we compare them, it gives you this array of Booleans, right? So it's saying that for each element, some of these are true and some of these are false, which is pretty cool because we can start using these to do whole array operations. We can use these to index into numpy arrays in a fancy sort of way. So let's do some advanced indexing. Yes.
In my particular case, I compare a lot what things lists have in common.
Yes.
Grab genes, they have these things. Okay, so
Right.
what things do these genes have in common? How do I compare arrays really fast to see what things they have in common? Not math, but
So this would be like you have an array, a bunch of G's, T's, and C's or something.
yeah.
And you want to make some metric for how close they are.
No.
Or just
Each element has a name. John, Bill, whatever. And I want to see the intersection of those lists. What they have in common.
right. So
This is an R, you find the magic index.
right. So I'll mention this is more sort of database kind of questions, right? I'll talk briefly about pandas, which is a Python library that builds on top of NumPy that does this kind of stuff very conveniently.
We'll talk about it.
Yeah. Okay, so advanced indexing. Right, so we mentioned multi-dimensional indexing. We can create an array that's multiple dimensions, and then we can access the first element, right? Which gives us, since this looks like an array of arrays, it gives us that first row, right? Familiar. You can also do slicing on NumPy arrays. So in this first case, so A of colon, comma 1, what that's going to do is colon is basically a wildcard. That it's going to say everything, but only in the first column. So if we print this, it'll go 1, 5, 9, 13. Right? Super handy. So also, right, you did slices like this with NumPy lists. That works. You can do strides. That works. So this is going for the first column, starting with 0, give me every other element. So 1, 9, and then I run out of the list. And then I run out of the array. Right? So, exercise for you. From what we've learned about slicing and indexing, print just the upper left border of the array that we define right here. Upper left. Yes. Upper left. So let's just print A. And so the part of this array we want are this upper left corner, so this 1, 5 block. And so we'll just start playing with things, print the whole array. And I'm not really sure which axis this is going to work. So let's just go 0 to 2, because there's 1, 2, 3, 4, and then the first 2. So see which side. Okay, got the right side. And then we can slice the other way, and we're good to go. Right? So, yeah, question?
The above 042, I don't understand.
So the 042 syntax, what this is saying is it's a start, a stop, and a stride. So start at 0, go until 4, and go in steps of 2. Yeah. Which is the same signature for range and a. So numpy arrays, for efficiency purposes, are when you take back up. When you take a slice of a numpy array like we just did, right? When you looked at the upper left corner, what you're actually doing is you're making a view of the same underlying table. And so what that means is that both arrays are pointing at the same place in RAM. And so if you change the array in one place, it shows up in the other because they're looking at the same place. And this is really convenient because you can have so memory allocation can be a significant performance thing. And so doing chunk allocations where you have everything in the same place on the machine will make your programs go faster oftentimes. But once you've done that allocation, you often don't want to deal with the whole thing. That's kind of a no. And so what you'd really like to do is just grab a piece of it and work on it locally. Grab a different piece of it. And so for this reason, numpy arrays, when you slice them, they give you views. And so what that means is if you created an array A, so where did it go? A is numpy A range of 16, 4 to 4, 16, and reshape it 4 by 4. Yeah, and B is upper left corner. Right, just like before. So here's A. Here's B. And now we change A00. And then print A and B again. And you see that it's changed in both places. Okay? Whereas, if you had done something similar in Python, so A list is 1, 2, 3, and B1 is A1, 0 to 2, print AL, that's a bad, A, I, So in this case, Python slices of Python lists return copies, which is different, right? So you just need to keep them straight. That slicing works different between Python lists and numpy.
What numpy array?
So if you want to copy, then you ask for a copy. Good question. So
do you have some transpose like it seems that your district column is in a row.
Yep.
So you have size very good and by one by n vector. Something like this.
Okay. So the question is sort of what's the comparison between MATLAB arrays and Python arrays is sort of what it comes down to. So in MATLAB, all arrays are 2D, whether you like them or not. And so there's a difference between a row and a column, because in MATLAB everything is actually 2D. Whereas in Python we actually have 4 real 1D arrays. There's no like hidden fake first in. And so in that case, so in that respect, Python arrays are different. Python arrays have sort of the functions you would expect. So it has a transpose, which is spelled .t, which is actually a free operation. There's no copy that happens there. You can just revert the indices and see the same thing. So the transposing is basically a free operation. Right? What's the other part of the question? That was close enough. So
whatever that.
Right. So if you so numpy has a linalg module that has determinants and Chomsky decompositions and eigenvalues, and numpy has a dot function which does the dot, the appropriate dot thing in the right context. You just have to go wander through them. But the point is, all of the common array and sort of matrix linear algebra kind of stuff you want to do is probably there. And if you need something fancy, SciPy does that. Okay, indexing. I'm running out of time, but as always. So before, remember when we did these array comparisons, right? You got this array of booleans, a bunch of trues and falses. Cool thing about numpy arrays is you can use that result to index into the array, right? So these start to look like filter operations. You can put masks on arrays and filter out only the pieces you care about. So let's look at this case. We're gonna, numpy has a random module, so we're gonna make a random int 0 to 10, print a, and then do this comparison of a is greater than 5, and then we can index by that. So what does that do? Here's a, and then we only get the elements then that are greater than 5. So it goes, call this mask, equals a greater than 5, print the mask, and then use, these will be different numbers because I'm calling random again. So you see, right, super handy, because you're going to do things where you're going to be pulling data from some machine, and there's going to be craziness, right? For whatever reason, the machine may give nans or -3 when the number should be voltage between 0 and 5, and you're going to want to filter things and slice and dice and stuff. And so you can combine masks, and so again, super handy. So let's run through the gotchas. We've covered each of these in piece, but let's collect them all together so they stick in your brain. Multiplication and addition are all element-wise. This is different than Python lists. So if you make a range of 5 and add it to another range of 5, that's a different answer than doing the same thing with lists, right? Lists concatenate. If you take a slice of a numpy array, you get a view at the same memory. So both objects are sharing the same memory, they're sharing the same data. Change one, it shows up in the same place. As opposed to slicing Python lists, which can be copied back. So one last thing. You can do math on numpy arrays, like I said, everything, all operations are array operations. So you take sines and cosines. NumPy has min and max functions. Arrays have min and max functions. All the sort of math you would expect, because it's built by people like us for people like us. So the things that should exist, and you'd be really angry if they did, are there, because someone has already been angry about that, at least in most cases. Universal functions, right? So you can take a log 10, that works, array oriented. Let's do, so that's NumPy. NumPy is an array package for Python. It handles arrays of homogeneous data types, and it handles them quickly. And if you're worried about interfacing with C and Fortran, it makes it super easy to do. Basically has the same idea of an array as it. So I'm just going to show you another Python library called pandas. So our users, what do you think of data frame? Like, greatest thing ever, right? Pandas is data frame and Python. That's how you should think of this. So pandas is short for panel array, multiple panel data, but pandas is a much cuter name. So, right. So I'm just going to show you a quick usage of some stuff you can do with pandas. I'm not a heavy pandas user. I'm sure all of you can think of other much more interesting things. But the idea is this exists. You should go play with it. So first example is I have a data file in that directory called parasitedata.csv. That's something with bugs. I don't know exactly what it's called. But pandas has a fast, very convenient CSV reader that will pull that in. Sometimes you have these CSV files that just have missing data, right? There's weird things. So I can tell it that an NA, right, a non-available data means string, or single. And so it'll go through, and instead of making all of your columns into strings, they'll be real numbers and with NAs. You want to see parasite. So if you just look at the first 10 lines of parasite, it gives you names for each of the columns and then data for all of them. They're just one. So if you print bugs, right, bugs is this data set we read in. That was a CSV. It tells you a little bit about things. There's a couple columns, virulence, replicate, Shannon diversity. I don't know what these things are, but there's some null values and virulence. The hard word. My apologies. But the rest sort of are behaved. We can ask bugs for the keys, and so it has these different columns. And then remember when we started doing filters on NumPy arrays? This idea that you can do a comparison for an entire array, and it'll give you back this Boolean array that you can combine with others to do some filters. Pandas does the same thing. And so, if say we wanted to do a histogram of the Shannon diversity, whatever that is, we can make one of these, right? So matplotlib has a hist function. And if it's now we decide that I actually really wanted only the bugs that replicate faster than 10 units, I can do that too, and it's a slightly different. So, right, this is starting to look like stuff scientists do with data, right? You slice things, you filter things, you look for parts in some ranges that I'm interested in, and all that's going on here is just a NumPy style comparison. That bugs that replicate gives you basically a NumPy array, and you filter, you get a mask, and then you apply that, and it works. And so the point is for this to be very natural and very easy. You can do normal operations. Okay. that's as much pandas as you really need to know. Well, as I'm going to give you, right? There's this. This is a great library. Go use it. And I think I'm done for time. So, any questions? Yeah. So the question is, does Python or pandas or something have an equivalent to our which command? And so what? So for me, what does the which command do? It would be right because I'm in the PDE world. Okay. I guarantee you, pandas does this. I don't know the answer. So yeah, where will give you the indices where something is true, right? Well, it'll return the actual indices. So if you want to say numpy as in p, numpy dot where bugs dot virulence is greater than 3. But not greater than 3. Greater than 0.7. It'll give you the array indices for all of them. But you could then print bugs dot I'm close. You can figure it out. That's the idea. That's totally doable. Any other questions?